Okay, let's start from the beginning. What's good, chat? I'm Enoch, and this is my brother Nathan, and we spent way too long learning how to build a musical instrument out of an old telephone. In this magical mystery circus, you will find music theory, programming, unmedicated ADHD. We're going to take you on a journey through time and space, but mostly time, so that we can intimately get familiar with symphony, its guts, how it makes you not suck at singing, open sauce, the science fair for adults, and demystifying the algorithm that big pedals keep under lock and key. The industry hates us for this simple trick. Let's dive in. This project started as, I'm sure we're all familiar with how all projects start. A dash of idea, an overwhelmingly amount of scope creep, and the rest is history. But it all started with a dream. I dreamed a dream of symphony, and in the dream the phone was singing. So let's talk about that dream. You can Don't encourage me. You can take an old microphone, and please do go on. Please. You can take an old microphone and turn it into a lo-fi mic just by talking into the speaker. And there were a bunch of videos of this a few years back. I was gonna play the video up there in the corner that I've hidden inside that phone, but the audio's not working, so instead I'll just act it out. And that lo-fi sound is beautiful. That's what we wanted to hear. And so I wanted to create that, and every microphone, or every speaker is a microphone if you just believe hard enough. Or just use it backwards. See, it's essentially a membrane that gets moved around by a magnet and a coil of wires, and if we just talk into the speaker, we're still going to move that magnet, it's still going to go past that wire, and then it's just going to run through backwards. So I picked up an old telephone from the thrift store and created this nostalgic monstrosity, but as I was looking at the rest of the box, I thought, after all, why shouldn't I? Why shouldn't we make the rest of this a fully functional instrument? But I don't know much about hardware, so I did what any sane person would do, and I roped Nathan into years of unpaid labor. We were able to hack together Synthphone V1. It's a lo-fi mic with some buttons that go beep, boop, 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 beep. But we just had a taste of that scope creep. And like the attic, we had to go further. What the heck?
It's playing video.
Oh, I see.
There we go. Next slide.
Besides, this project really deserves to be a vocal processor, and if you don't think so, you're either my brother and you want out of this carousel of never-ending features, or you're lying to yourself. But look at it. I mean, it's a microphone attached to buttons. It's indistinguishable from these vocal processors you see here, other than it's red, which is cooler. So for version 2, we decided we were going to need 3 key features. First, automatic tuning. It's going to be a whitelist of frequencies that we allow you to sing, and then we round to the nearest frequency in that whitelist. Formant shifting, which is taking the spectral envelope independent of the frequencies and shifting it up and down to sound more masculine or more feminine. And vocoding, which is applying that spectral envelope as a modulator on top of a carrier wave, which is commonly a saw wave, such that it makes the saw wave sound like a human voice. I'm going to go into each of these in more detail, so don't worry if you don't understand that right now. But it's one thing to process audio when you know the full picture. It's a whole other thing when you don't have all of the data at the start. And so in order to process the audio in real time, we can't process one sample at a time because that's just amplitude in a single point in time. Rather, we need to get a window of samples so that we get a good idea of what's involved. To do this, we're going to need two circular buffers, one to collect samples until we have a large enough window that we can send it to our block-based processing, and another to take blocks of samples and just spit out one at a time to give instructions to the speaker. After we process each block of audio, our phases might not get aligned. So what we need to do is sample more than we need. We're going to hop backwards, and you can see it in that image in the top left. We're going to hop backwards and sample what we've already sampled, and then apply this Hahn window or Hamming window, whichever one fits your use case best, as a sort of crossfader so that we can always keep an aligned and don't have any jumps in the processed audio. This is referred to as constant overlap add, or the COLA constraint. And then, before we can think about tuning, we're going to need to find out what note we're singing. To do this, we need to extract frequency information using a math algorithm called the fast Fourier transform. This gets us into the frequency domain, where we can see the fundamental and resonant frequencies. It works like this. Audio waves are essentially just amplitude over time, and we can see in this example, in the bottom left example, we can see kind of an oscillating wave. Let's say that's A at 440 hertz. And we can count the peaks and troughs, and we can, see that it's oscillating at 440 hertz. It's giving that instruction to the speaker to push the air back and forth. But humans don't speak or sing in pure sine waves. When we sing, we create a fundamental frequency, but our vocal cords resonate at integer multiples of that fundamental, creating the resonant frequencies. And because waves are additive, when we sing, the peaks that line up get peakier, the troughs that line up get troughier, and the peaks and troughs that line up kind of cancel out. In that case, in the middle, we can see those three sine waves adding together to create the complex wave that we see before there. So in order to extract that complex wave, we run the fast Fourier transform, and it gives us something like this bottom right graph here, where we can kind of see where in the frequency domain we have these peaks. That's where the fast Fourier comes in clutch with these window of samples. We want to grab a big enough window that we have a good idea of the wave, but a small enough window that it's not going to introduce latency. And then we can synthesize a new wave by doing all of that backwards. So once we are away from the time domain and into the frequency domain, we can manipulate the frequencies how we want. If you want to pitch the voice up an octave, you just multiply every bin by 2. If you want to go down an octave, we just divide all the bins by 2. In order to do automatic tuning, first we need to find out what note we're singing still. So to do this, we get, you can kind of see it at the top right. I guess it's a little too small to see, but we downsample a couple times and keep track of where the frequencies line up, and that is going to show us where that fundamental frequency is, because it's integer multiples of the resonant frequencies are integer multiples of the fundamental. So once we have the fundamental, we we can take that and see how far away it is from our white list of frequencies, and then just shift up or down depending on whichever is closer. That's not the whole story, though, as the bins that we get from the FFT are not lined up to the keys on the piano, but they're relative to how big your FFT window is. And so you have to do a little bit of math keeping track of the phase from one frame to the next so that you can get an actual idea of the frequency. But now that we have that, we can keep our voice in tune. Next feature is formant shifting. But to do this, we need to understand what even formants are. So formants are often associated with the creation of vowel sounds. Sound science has showed us that each vowel seems to retain a spectral envelope. In other words, this general shape, independent of the lines that we see underneath it. It's that dotted line that's going to stay the same. This is generally why we can change the pitch of a vowel without changing the shape of our throat. Formants are more than just vowels, though. Formants are what give sound its timbre, or flavor of sound, if you will. It's the reason why a trombone and a flute can play A at 440 but still sound wildly different. They each have different general shapes in the frequency domain. So let's learn how we can change the flavor of our voice. Formants are created with the shape of our mouth and vocal cords. And this is how we shape the spectral envelope of the vowel sounds that we create. There are four main peaks in a formant, F1, F2, F3, and F4, and they're grouped together usually, F1 and F2, F3, and F4. The first thing that you'll notice when shifting up an octave is that you sound like a chipmunk. And this is because we're not only shifting up the frequencies, but we're moving that general shape along with it. So if we take a look at this top image here at the very right section, we have some sound that we've created, and then we pitch everything up. So what was 4,000 is now 8,000. What was 2,000 is 4,000, and so on. But the shape has changed. And so we want to apply the original general shape to the new frequencies, which are the lines that we see there. When we do this, we can pitch it up while maintaining a human kind of voice. But we can do this more than just pitching up to fix chipmunk sound or kind of deep bank robber voice. You can also just shift it up or down as you please to make the voice sound more masculine or feminine. To extract the original formant, we need to do yet another Fourier transform, if you can believe it. So this time, we need to take the log of the frequency spectrum, do the IFFT to it, and this gives us into the cepstrum. Can anybody tell me what the cepstrum is? That's because it doesn't exist. It's spectrum spelled half backwards, because it's not real. It's a spectrum of a spectrum. But what it does give us is the presence of these formants. So once we have the presence of these formants, now we can shift the formants around as we please. And to reconstruct it, we just do everything backwards again. So that brings us to vocoding. And with all these building blocks laid out, creating a vocoder is going to be relatively simple now. We just need to apply a formant filter on a computer-generated wave. If you think of Autotune as being a human sounding more robotic, vocoder is a robot sounding more human. So to do this, we have two main parts, a carrier wave and a modulator wave. The carrier wave is the robot's voice. This can be anything from a sawtooth wave a square wave, really anything with resonant frequencies. So a sine wave is out of the picture because that's only going to create one peak in the frequency domain. And there's not going to be anything to shave off or amplify. So we just take that carrier wave and we apply the formant of the human's voice onto it. And then we can sing around the world 300 times and we got an instant hit. We are now feature complete. But then I thought, maybe we could move this goalpost just a little bit as a treat. So what if we added a harmonizer? Since it's really not feature complete until you can sing Hide and Seek by Imogen Heap, right? Until you're singing What You Say in it, I don't think it's a real... But then we were saved by the deadline of open source. Our saving grace from scope creep. This gave us a deadline and forced us to lock in on features and fix bugs instead of following the dopamine. Open Sauce is, as you've heard, an adult science fair. It's in San Francisco and features maker YouTubers and inventors of all sorts, from BattleBots to motorized chessboards. There was even a fully functioning 6-foot Wiimote that you could play Wii bowling with. Whether it was, innovative or unnecessary, fun or frustrating, musical or noisy, Open Sauce was the perfect place to show off our hard work that we put in. So, did we actually go there to meet Mark Rober? No. But did we happen to meet him while we were there? Also, no. Keep up. But there were tons of creators that are huge inspirations of ours, and we got to show them off Symphony, and we got to show off our product, but not as intimate as you're about to see, because Nathan's here about to show you its soul and its guts, but mostly its soul. It's actually more difficult than you might imagine finding an automatic tuning algorithm, because these big companies, they're keeping their bread and butter under lock and key, and they like to gatekeep. So we open sourced it and released it from its shackles so that anyone can do it, and Nathan's going to dive in on how you can make your own auto-tuner. And I'll switch it over to... Give it up to Nathan, everybody.
Okay, so yeah, do you want to hook up the...
Yeah, I'll hook it up and you
Sweet.
go over yours.
So we will try to go through somewhat of a live demo. When we started this project, we were faced with our first obstacle. That was, what were we going to write this in? My brother said, hey, let's do it in C++ because that's what it's always done it. And I said, well, C++ is no fun, let's use Rust. And so that's what we did. And to kind of give you a taste of what that is like, we're going to have I'm going to show you the basic setup of Rust, how to get Rust installed, how to do embedded programming in Rust, and then at the very end, we're going to have a working auto-tuner that the people here will hopefully be able to hear, and the people on Twitch will miss out on because we couldn't figure out our audio stuff beforehand. All right. So let me mirror my display real quick. Okay, so to start off with, we had to choose a microcontroller, and we decided to go with the Daisy Seed. Why the Daisy Seed? Because it is pretty much built for our application. This microcontroller is running a ARM Cortex M7 MCU running at 480 megahertz, which is really necessary for the amount of processing that we are doing. For for those who have never seen the daisy seed, it looks something like this. This is the pinout diagram. It looks a lot like an Arduino, except it's got a lot beefier of a processor that it runs. And for this demo, this is kind of what it would look like if I wasn't using our already built PCB. We have the device, a speaker, a mic, and then that red square there is a preamp that we had to install for our application because we're using a speaker as our mic, which has its own problems. And this preamp we bought off the shelf fixed most of the problems we've run into. For anyone who cares, this is what the schematics of our PCB, that this phone looks like. And it's the same thing as what you saw up above, but with some more components added that allow us to do other things like push buttons and twist encoders, and hopefully one day we hope to add a MIDI device. So Rust is pretty simple to set up. The first thing that you have to do, obviously, is install Rust. Rust Up is the tool that you use to install Rust, and for Mac and Linux, it's a simple one-line command that installs it and gets it all ready. For Windows, it's a installer, as Windows likes to be. So we have way too many windows open. Okay. So after that, we can confirm that we have Rust installed by using the rustc command. And I'm running Rust 1.89 for this demo. The next thing we have to install is the toolchain. Rust needs to know what it's going to compile against, and in this case we're using the Thumb v7em with all these other settings. You might be wondering, how did we find out this information? Well, the first thing we do is we know we're running a Cortex M7 for a processor, so we go to the ARM website to find that. Here we can find the exact architecture for that processor, and we can copy that. And then we can see that the ISA support is the Thumb or Thumb 2. So now we can, now we can go to our platform support, and we can find that on this page. We see that there's two options. There's one with a hard float, one without a hard float. I know that this specific device is using a hard float, which is kind of necessary for the amount of floating point processing that we are using for our audio processing. All right. The next thing we have to install is probe RS, which again is a simple one-line command. It's kind of the great thing about Rust is things are pretty easy to install. And once we have probe RS installed, we're able to debug and load our application through the ST-Link. And that communicates directly with the STM32 hardware, as would if you worked with STM, you probably use the STM Cube. This allows us to run the program directly from the command line without using that GUI tool. And then finally, we have LLVM tools and the cargo pin tools, and that allows us to do some more debugging and helps us run the device a little bit. And then finally, there's a bunch of great resources for learning Rust as well as learning embedded Rust. I highly recommend the Rusty Bits if this is something that you're actually interested in getting into, is doing Rust on embedded device. This is a C++ developer who used to write embedded systems who is now switching and teaching people how to do that in Rust. So let's actually write some Rust. So Cargo is like the NPM version of Rust, if you're familiar with node packaging. We can do oh, I lost the mic for a second. Cargo new, and then we'll just call this mic demo. I actually might have already have that. There we go, mic demo 2. And then we will go into mic demo 2. And then let's open that up. So Rust has the basic, the mic's all over the place. This is our basic Rust project, and we have a cargo toml. This is like your package.json or your Gradle build file. Then we have our source, and in source we have the main file. This is the entry point to our application, and in there we have just auto-generated this main println command with the hello world. So from here, we can do cargo run, and this will run our program. As you can see, we have hello world printed at the bottom. So this is our first Rust program. Now, if we want to do embedded development, we can specify specific targets. So we can say -target, and then let's grab that target and plug that in. And when we run that, now we're getting errors. It doesn't work. And this is because we can't find the crate for the standard library. When we're working against embedded devices, we don't have access to a bunch of the standard library features, and that's because we're limited on the amount of processing power that we have. The standard library is just cut from what we have available. So in order to fix this, we would have to get rid of this line, as well as specify that we're not using a standard library. We can do that with this right here. Anyway, so from here, we can then start to build out our embedded processing development. For the sake of time, I'm going to switch over to the repo that has this already set up so that you don't have to watch me type all of this out. We're going to cd into 3. Okay. So here we have our boilerplate. So there's a couple new files in this project that we hadn't talked about before. The first one is this memory X file. Our program doesn't know exactly what memory we have access to on our embedded device, so we have to specify what the memory looks like, how much we have, and where it's at. So this is what that would look like, and this is usually something that you can find if you look at the specifications, and the Rust community is really good at getting this information to you. Then we have an embedded.toml. This is used for our debugger. This tells our debugger how to connect and what debugger to use so that we can get our logs into the console. We've got our updates to cargo toml, and so here we've added several new crates. We've added the Cortex-M RTIC. RTIC stands for Real-Time Interrupt Control, and that's the main library that we're going to be using for our operating system. There's really two main operating systems that you can use in Rust. There's the RTIC or Embassy. Embassy is kind of the more popular one, but when we started this project, Embassy wasn't really an option for our device, and so we went with the one that was ready, RTIC. The Cortex-M is our bare metal information about the device that allows us to access registers and things like that, as well as this STM32 Hall. This is the hardware abstraction layer for our bare metal so that we can have a little higher level functions for accessing our embedded device. We have log, which allows us to log to the console and get that information. libdaisy is the library that is kind of built on top of the hardware abstraction layer. This allows us to do all the stuff that's specific to our device, the Daisy. And this device is, as you can see, this is a GitHub link. I had to fork it in order to make some changes that was required for our application. Finally, when we get to it later on, there's a synthphone vocals. This is a work in progress of our open sourcing of the Autotune library so that we can do the Autotune without going through the hassle that Enoch and I had to go through in order to get that to work. And then finally, these are the configs for the compiler that lets us know how we're going to compile. This LTO true is necessary for our device because we need it to be optimized whenever it goes onto the device, or else we get bad audio, sound, and bad processing. Here in main, let's go to this config file before we talk about main. So in the config file, we have a target and a runner. This runner specifies that we're going to use probe.rs, and then with those specific commands, whenever we do cargo run, and that way we can program our device with probe.rs, and it automatically hooks that in, and we can still use the cargo run command that we're used to. These are flags that are being added to that command in order to tell what the linker needs to do. And then this is our target at the very end that we're building for. So we can run this. No, we should talk about what's in main first. So RTIC Real-time interrupt control is a concurrency real-time processor. It allows us to make tasks that the device can run at specific intervals, or you can kick them off. It can happen from an external trigger, that kind of thing. And so here we have access to two arrays. One's a shared and one's a local. And these structs define what kinds of data is going to be used for those tasks. Shared tasks can be shared across anything in the shared can be shared across multiple of the tasks. If it's in local, it can only be shared. It can only be used in a single task. And then we have, by default, two main functions. Our init, this runs every time the device boots up, and our idle, which runs anytime there isn't a different task running. And so for now, our init's just going to start up the logger. It's going to log something, and then it's going to be done. And then it's going to kick off to the idle, and then that's going to be done. So if we do cargo run, right now it's programmed the device. So now it programmed it. We get some information about what the setup was. This is coming from our libdaisy. And then we have our system init done. And for some reason, the device did not go into idle. That's okay. How are we doing on time?
We're good.
We're good? Okay. So from here, we can add in our Autotune abilities. So, I guess before we do Autotune, we need to...
Can you make sure that it's like plugged in here?
Yeah.
If you're like bumping that, that could be a problem.
Possibly. Okay.
Is that coming through?
Yeah, I think so.
Cool.
All right. So the first thing we need to do is set up our pass-through. That's kind of like the hello world of the Daisy seed. This is the audio is going to come in through the mic, and then it's going to go through our device and come right out the speaker. And so we have to set up a few things to get pass-through to work. The first thing we need to do is add our block size. So we have const block size. And this is going to define how big of chunks we're going to put in before we spit it back out.
And you'll see some kind of things that we've talked about earlier come through in this demo here.
Yeah. So the next thing we need to do is define two resources that we're going to access, and that's audio, and that's going to be coming from our libdaisy library. And so we are going to grab audio from there and a buffer. And the buffer is going to be our max buffer size that we can grab. And this is also coming from libdaisy. Audio buffer. That's not the one I wanted. Okay. So from there, we need to initialize these resources. So in order to get this to work, we need to actually start up our device. So we have to do a couple of things before we can even get audio out. And that is that we have to set up our core. So in Rust, everything is immutable by default. And I think it's just flopping around. Everything's immutable by default. And then if we if we say mute after the let keyword, that allows us to access and change that variable. For this, the core, we have to have it mutable when we grab it. The next thing we need to get is the device. And this is all stuff that's necessary in order to start up the libdaisy library that we pulled in through cargo.toml. We need to set up the clocks. That's system.
And the great thing about Rust, as you've seen way earlier, is that anytime we mess up, it's going to give you a nice list of not just like, hey, something went wrong, figure it out. It'll give you a nice list of like, hey, maybe try this. Maybe try adding the no standard library tag if you don't want to use it. And then we can kind of use that to see, oh, yeah, I didn't want to use that. I'm using embedded.
Yeah, and Enoch, again, he had never used Rust before this.
And I didn't want to.
And he didn't want to. But So while we were talking about it, I was like, okay, we'll set both up Rust and not Rust, and if
Yeah, we did a contest to see who could spin one up faster, C++ and Rust. He blew me out of the water, so we had to use Rust. We get to you. I'm coming around. It's been really nice.
So here we're initializing our system by calling this libdaisy, and we're passing in all these into this. This is called a macro that has this this right here denotes that this is a macro, and so this allows us to do a bunch of code in the back to get this to work, so that we don't really have to think about it, and we set up the system that we can now pass in, and then we finally have to set up the buffer. Sometimes the autocomplete works, and sometimes it has no idea. And then from here, we are going to set a tuple that is of 0, 0, and that is going to be equal to not buffer size, but our audio block size. And finally, we can pass those into here. We get audio, and we set that to system.audio. This is coming from libdaisy. And then we can pass in the buffer. And we'll go ahead and do that. And that should be, and there our error went away. Now we need to make a new task. This is going to be a hardware task. It's an interrupt that's going to happen every time the audio buffer is ready to process the audio. And so we have to set up this task like so. Binds. Then we specify where this is happening at, and this is going to happen at DMA1_string1. And we're going to grab our audio buffer from local. I'm going to call this audio handler. And then we're going to get the context from audio handler. And then from there, if I didn't forget anything, we need to grab our audio again. This comes from our context.local.audio. And let's grab our buffer, also from context. So this context object is keeping track of all of our shared and local memory, and then we can grab it to be used. That's there, and this needs to be mutable, I believe. Or not.
So once the hardware has enough samples in that block, it's going to run this audio handler. And then we can take that and kind of loop through each of those samples.
Okay, there we go. The autocomplete again set me up for failure. So the next thing we're going to do is we're going to grab that audio, and we are going to grab it from the buffer. And if it fails, we're just not going to do anything. So that's what this if we'll check, and if we're able to grab the stereo, then it will process what's inside of the curly braces, and if we're not, then it won't. And then from there, we can loop through our buffer. And we're not going to loop through it like that. In our buffer, we're going to grab it as a slice. And we're going to go up until the block size. So this is, we're going to process the audio at every block size, and then we're just going to push that audio back out. And so we pass back in that tuple. We're going to just pass in the right side, because the way this the way we set up the PCBs, we have two different channels, one's left, one's right, and we're hooked up just to the right channel. So we're going to push that both out, the left and right outputs, so that we have a solid audio coming out.
It's a mono signal, so we just use the right channel for the telephone, and then we have the left channel be for an external mic that you can plug into the device. So for this, we're just going to put out the right channel from the handset.
Yep. So from here, so this is our code. If the audio fails, then we'll get this info log, which I don't perceive us actually ever seeing that. So now if we run this, we're going to program it again. And it looks like it works. Enoch, do you want to?
Yeah, let's create this.
I hear something come out. Okay, so as you hear, we have audio. It's going through here, passing through our Daisy, and it's now coming out the microphone on the other end.
Can you guys hear that in the back?
So now for the sake of time, we're going to go to our Autotune version. Sorry. Did I? Okay. And so here on the other Autotune version, for the sake of time, it is cutting in and out. I'll just take the mic.
Yeah, sorry.
And I'll turn this off. All right.
Here, switch me. He's got 2 mics. And I got 2 mics.
All right, is this work here? Check. Hello? Yeah, you can hear?
Can you guys hear that in the back?
Okay, sweet. So from here we can, I meant to pull up this joke earlier. So back at the README, if we looked at the very bottom. So this is kind of the demo that we're doing. I'm drawing a horse, so I'm going to show you the circles and the legs and the sticks and whatnot. And then at the very end, we're going to add the fine details to get Autotune to work. So that's what's going to happen here. So here we have our Autotune app. So the cargo toml didn't change because we had already added unnecessary libraries to the previous one, but we have changed quite a bit that we're going to be using here. So we've added in our 2 buffers. As Enoch had mentioned, we're going to use an in buffer and an out buffer, and that's to be able to load that audio both as it comes in and as we auto-tune it and then spit it back out. We have to have a pointer to those buffers. Now, I will point out that right now, the only unsafe code in this project is in our ring buffer. And that's because we ran out of time and open source was coming up and we really needed it to work. So we did what anyone does and we wrote code that accesses memory without checking it correctly. So
You get the job done.
yeah, that's right. So
Safety third.
it's a podcast. So we have our FFT size. So we have a couple of different sizes that we're going to define here. We have our FFT size, and that's the size of our FFT that we're...
Yeah, that's the window size of the FFT that we're going to process.
Our buffer size is going to be 4 times the buffer size, and that's just to avoid...
We need to fit a bunch of samples from that FFT, and so our block-based processing is going to need to be a lot bigger than the block itself, because then we're going to run into overruns, and because it's a circular buffer, it's just going to rewrite on top of itself, and you'll not be able to figure out why it sounds like garbage, just that it sounds vaguely, you remember that sound previously. Or you're just going to mess it up in weird ways. So yeah, we have to have that as a ridiculous number.
Yeah. We have our hop size, and Enoch mentioned this earlier, but we can't actually process the whole audio at once because audio happens over time, and if we processed everything that's being said after it's being said, then it's a huge delay. So our hop size has to be a fine window between how fast can we do it and how much data can we get in that hop size. We found that 256 was kind of a sweet spot for us that made it so the delay wasn't too noticeable, but that we were able to process the audio and not get an output that was too messed up. Because as this, we're applying a Hanning window to that, the Hanning window?
Yeah, a Hanning window.
To that, which kind of smooths out the edges and tapers it so that there's not jagged edges when we compare those.
Yeah, it just acts as a crossfader between the oversampled pieces. So in the picture, if you remember before, it was every half it was oversampled. But right here, I think we've got every, we've got it oversampled 4 times over. And then we're just smoothing it out by adding that window on each and just crossfading the data.
Yep. So then finally we have the block size, and this time we've put the block size to 2, and that's because we want to get the audio out as quickly as we can. We don't really need to wait for it because we have a bunch of other things happening that's already causing our system to wait. So if we then continue on, we have a bunch of stuff in our local array as well, and so these are static memories that need to be remembered between each run of the task, but don't need to be shared between multiple tasks. So most of these are actually going to be used in our Autotune task, whereas the ring buffer and out buffer are going to be used in both our Autotune task and our audio processing task, or our audio handler task that we had written earlier.
And our auto-tuning task is going to be that block-based processing that only happens every now and then when we have enough samples to do something with it. And then the other handler functions are going to just run and spit out audio and collect audio.
Yeah. So now if we look at that audio handler that we wrote earlier, we have a bunch of new things added to it. So the first thing we do is we're now grabbing the sample and we're storing it. And then from there, we are grabbing the sample and we're sticking that into the ring buffer. And so this is as we go, we're putting audio into the ring buffer, and then we're grabbing audio back out from the out ring buffer. This out ring buffer is the audio that is being auto-tuned. So that once it's auto-tuned, we grab it out from the auto-tuner. Then we normalize that. You're gonna.
Oh, I was just going to say, so there will be a delay that's, I think it's 1 hop size or...
It is, yeah. We have to process 1 hop size before we have any data, because before that, it's just zeros.
So that output buffer is just going to be a hop size full of zeros, and then it's going to start having data because of the way that we need to wait for a hop size before we can process anything.
From there, we count up our hop size. Once we hit the specified number that we specified at the top, we trigger off our auto-tune processing task. If this task happens too quickly, we get an overrun error where it can't process it fast enough to finish, and then we have an issue where we're trying to spin off a task that already is currently running. And so that's also part of why the hop size has to be the size that it is. So from here we spawn the auto-tune task, and then we just continue and we push the audio back out.
And you can play with those sizes depending on how much processing you're doing. You'll have to find the sweet spot for you, but this is what we found for our processing.
So from here, we have our auto-tune task. So this is a software-defined task. It's not triggered by an interrupt or an external input. It's actually triggered by us, by our software, and we spawned this manually, as you saw earlier in the handler. From here, we have our different auto-tune settings. So we have our musical settings, and that's right now we're setting it to default. This is the key octave format and all that, so that we can change our pitch and our key and so on. Where on our actual device, you're able to adjust that with the wheels. Since we don't have buttons and we don't want to spend the time to set up buttons for this, it's just going to be static for now. Then we have our config, and this just specifies things like sample rate and FFT size and so on. This part is still a work in progress, and it doesn't actually do anything right now.
We'll clean it up later.
Yeah. Then we're copying everything into this input buffer, and then we're writing it into the pointer, into our ring buffer here, and then after that we just auto-tune everything and we stick it out, and that's it. That's how you auto-tune. I'm just kidding. There's a lot that we've abstracted out of this. So if we go into the actual Autotune function, you can see that there's this wall of different arrays that have to be made. This is because we have to keep track of what our phases are, what the phases are changing to. We have to keep track of what the audio, what our magnitudes are, what our synthesis output is and input is, and so this is where that all happens. So here we've again abstracted everything out into our FFT analysis. That's our first step, is that we need to find the frequencies that we have. From there, we do our septural analysis for finding formants. Then we calculate our pitch shift ratio to know what we need to move in order to auto-tune correctly.
Yeah, the ratio of how far we need to jump.
Then we have to apply the spectral shifts so that the voice sounds a little more normal, or less normal, if that's what you're looking for.
I prefer the less normal.
And
Just
then,
make it sound real weird. But there's the options.
And then from there, we do our synthesis. So if we go further into this, the analysis, we're using a library, micro FFT, to do the FFT analysis. And then we're doing a bunch of math to get the frequencies, and we're saving that into our last input phases that's going to be used by the next function. The next function is our analysis that, again, is running through everything, running the FFT again. This is several processes of the FFT that goes on, and this costs a lot of processing power to do these FFT functions, and as many as we have to do in order to do all this audio processing. And
yeah, the fact that we have to do it 4 times, 2 times per, you have to do the FFT to get the frequency, and then another FFT to get the substrum, and then once you're in the substrum domain, you can do your liftering, which is just filtering spelled backwards, and then you do the FFT to get it from the substrum back to the spectrum, and then to the frequency spectrum, and then an inverse FFT to get it back to a wave. So 4 is a lot, so we had to pump up the processing there.
yeah, and all of that happens in less than 30 milliseconds. Anyway, from there we do the opposite, and yeah. And you're welcome to look through this if you'd like. It's quite a bit of code. But we'll go ahead and show off what Autotune is like. And by we, I mean Enoch will show it off.
Oh, okay. Oh. Hello, devs, Springfield devs. Am I singing real good now? Can I sing?
And so yeah, that is how you make Autotune on a small embedded device.
I got a last slide, but again, I still don't want to touch the Mac. So if you could do that for me, that would be great.
Oh no, I closed out your slide.
You closed out my slide.
Oh wait, no, wait. Yeah, I did.
Yeah, it's gone. He's had it out for my slide since day one. Command Shift T.
Command Shift T. What we're going to do. Nope. You know what? You don't need your slide that much.
I do. I want my slide.
That's okay. Yeah. I swear that I know how to work a computer.
Click on your window for the browser.
Yeah, got it.
Jackson, you're trying too hard.
Oh, look at that.
Oh, look at that. It works. And nobody said that out loud. He just thought of that himself. Ooh, we're going through space and time again. Thank you. No, but for real, if you guys are interested in any of the stuff we talked about, we have a video on that website, and in the description of that video are all the links that made us understand what's going on under the hood. And so if you want to dive deeper, we've got all those resources in that video link. But yeah, I think we're able to open it up to some questions if
Yep,
anybody
I will
has
bring
any.
the mic to anyone who's got a question. All right, number one up front here.
Hello. Did I see a MIDI port on the back of that thing earlier?
Yes.
And if so, what is the functionality? Can you control like the vocoder
So-
audio processing parameters, or?
You remember the part where Scope Creep came along and showed its face?
So like a week before.
So like a week before, we decided we wanted to add in Autotune or add in MIDI functionality. So eventually it's gonna be where you plug in a MIDI mic.
Eventually, it's going to be where you plug in a MIDI mic, and then it's going to affect the. So if you're vocoding, you can play the chords, and it's going to play the saw wave, and you can vocode that. We are like halfway through that harmonizer that I talked about. So then you can sing Imogen's Heap, Imogen Heap's Hide and Seek. So you can go, what you say? And then we want to open it up to where you can just have, MIDI CCs to affect the format, the pitch shift ratio, and just all of the settings that are under the hood. We want to expose those so that you can control it with a MIDI keyboard. But again, that was Scope Creep that we started like a week before open source, and then we finally came to our senses and realized, we need to fix all these bugs.
Yeah. On top of that, the
He's got a mic.
yeah. MIDI requires extra processing power that we're going to have to find out where we're going to get that from.
And we will.
I turned my mic off.
All right, I got a two-parter here for you. So
Okay.
obviously, there's a lot of really interesting parts of this whole mechanism. What was the most difficult hump to get over in terms of this learning curve?
You want to go? You do one, and I'll do one.
So just getting vocoding working the first time to kind of as a proof of concept that we could actually do this on this device. We followed a guide that had a device that was like twice the resources that we have. And so we really worried that we weren't going to have enough resources to actually do this on the device that we did. So on top of that, Levi thought that, he's like, why are you guys spending so long on this? ChatGPT could do this in an hour. So we spent about 3 months, so it was only Fridays, 3 months, Fridays after work, working on this. Levi thought ChatGPT could do it in an afternoon and managed to get something that didn't even put out an audio file correctly.
Put it on an audio file. It just sounded like this. Which is what I sound like sometimes. But then I slapped the autotuner that works, and I sound great. It was the vocoder, and it was not for the reasons you think, because the autotuner was, it was mildly, it was more difficult than I thought it was going to be. I was like, auto-tuning is easy. You just take the note you're singing and make it the note you want to sing. But then I was like, what note am I singing? And how do I shift the notes now? And these bins aren't piano keys, so how do I figure that out? So, but the vocoder, the reason it was difficult was just an issue with this ring buffer class that we wrote to try and save us some time. So I ended up just having to go back to I tried following it down like line for line, like I'm a bit in this machine and I'm going to find out where I end up. And then I was like, it all makes sense. It should work. And so just scrap the whole thing and rewrite the buffer class. Which is stupid. Buffer class should not have been the hardest part of that, but it threw the biggest wrench, I guess. It wasn't the hardest, but it threw the biggest wrench.
Because it should have worked.
All right, and the second part to my question is, can you play Wonderwall?
It's on
No.
the code right now. This one.
Maybe. No, it's not plugged in.
No, it is. It's just
Oh.
your dumb.
Oh yeah. You gotta know how to work it. It sounds sickly.
It does.
It doesn't always sound like that. I swear, this never happens.
That actually kind of answered my question. I was wondering if you were going to use like the dial tones on the keypad to play notes.
Yeah. So it has a way to kind of change the key, and so you can switch the key, and one is going to be your root note, and then it's just going to go up from there. But you can switch that, and that's going to be the same key that you play in when you're in synthesizer mode, but then you can shift it to vocoder mode, and now you're going to sing in that key, and then it's going to automatically, well, just show a little bit. You want to hold this?
Yeah, I will say that the actual dial tones for the phone sound pretty bad, so we threw those away. We had originally done that, and then we did it, and we played with it, and we were like, yeah, this is not fun.
Okay, something's severely broken about this direction.
Oh. That's funny. Here, let me.
Anyway, you can change the key. In version 1, we had mode control, like your musical modes, but we found that not many people. Can I cuss? Gave a shit. So we just have major and minor, and then the rest of the keys.
It might be a silly question for me, but what exactly is embedded coding programming? So is that literally, just from my understanding perspective, it's just an external program you're calling?
So embedded programming seems to be used in multiple different cases. In this instance, I'm talking about using like an embedded system, so like an Arduino or a Raspberry Pi or so on and so forth. And so we inside of here we have this small computer that's running a microcontroller that runs at a single core that we're putting our code in, so it's embedded into a PCB.
Is it fair to say that a lot of embedded systems is like programming without a real operating system?
Yeah, and you have to worry about things that you normally don't have to worry about. You don't have the luxury of a garbage collector, so you have to worry about how your memory management works, and sometimes you can even get down to like pointers and different bits and how this bit affects the whole system. You have to configure bits and whatnot. It's a fun way to program things if you really like to get into the weeds of operating systems.
And then sometimes you can get even further down to like have to know how far you're when you're mapping the what are the traces on the PCB called? When you're mapping those, you have to
The traces.
they're the traces. You have to measure how long they are so that they're coming at the same time. We didn't have to do any of that, but that's something in embedded systems that you can get into.
So you said you had to do like 4 FFTs?
Yes.
So are there any optimizations you could make without sacrificing quality, like reusing an FFT at some point or something to make this run even faster?
No, you can't reuse it because it's based on the FFT that you just did, and so it builds upon each other. And the reason it's 4 is you got this building block of the first FFT to get the frequency domain. The second FFT, or it's actually a little different. It's the log and the IFFT, but gets you into the Cepstrum domain. And then once you're there, you want to go back. So now you got to do the FFT. You did the inverse FFT. Now you got to do the FFT, and then you got to do the inverse FFT, and you go up and back down, and then you got a wave again. Start with a wave, end with a wave, and that's why you have to do that. Now there are other algorithms you can do, but they do sacrifice quality. So you can do a time-based algorithm, but you're going to that's going to be like what you see in those Halloween voice changers. It's going to be probably going to be a time-based algorithm that doesn't take a lot of processing, and you don't have to do an FFT at all.
I will say, to add on to that, that the library that we're using, the micro FFT, is optimizing a little bit. It's got a bunch of, so in embedded systems you kind of have a trade-off. Do you process it or do you store it? And so lookup tables is really big in embedded systems, because if you have the extra space, it's easier to create a lookup table that then you look up the answer as opposed to actually doing the processing. So this one is optimized for lookup tables. So for some magic that I didn't bother to look into, it's using lookup tables to process FFTs.
All right, this is probably going to be our last question, and then more at the after party.
Sure.
Okay.
All right. My only question is, does it bother you that you did all of this work to do all this vocoding off of that kind of microphone? It feels like nuking an anthill, and I love it.
Well, I am a huge fan of hyperpop, and the kind of aesthetic is like, the nostalgia core, shitty sounding audio in a cool way. And so let's take a microphone and shove it all the way down our throat and see what that sounds like. Oh yeah, that sounds awesome. So the fact that we're using this mic is the charm of it. You get that nostalgic, I'm talking on an old telephone. And then we've also got, here, will you hold this up? We've also got, which one is it?
This working? Okay, where's on the vocoder? We've also got a sound worse. Or you can make it sound less worse, but sound like it's coming from an old telephone.
Or like an airline.
And then, you can pitch it up, and you can't pitch it up. The top buttons aren't working, but that's okay.
But yeah, I am not sad at all that we're using a shitty mic to do all this audio preserving processing. But there is a saving grace, because we have that second port on there. If you want to connect an actual good mic, you can do that. And then we have it to where as long as the phone is hung up, then it's going to run through that one. But when you unhang it, it's going to run through the handset.
Yeah, so if you remember, I had the right and left, and I only used the right channel. The left channel, we have this wired, would be that other input, and so that's why we only used one side of the audio input.
All right, please give them a huge round of applause. That was amazing.
Thank you.
Thank you.